Every half reaction has a standard reduction potential, the voltage of that particular half reaction at standard conditions. Sometimes it's represented like this, but most of the time you're going to see it referred to as standard reduction potentials. I'm going to hand out to you, or I may have already handed out to you, a standard reduction potential sheet which is given to you on the free response section of the AP exam. Because every voltaic cell has two half cells, two half reactions happening, it's not really possible to measure standard reduction potential for a half reaction directly. So what they have done is they have assigned a standard reduction potential as a base, as a standard that everything else is going to be referenced to. They chose hydrogen as their standard, and they kind of did everything else around hydrogen. So they gave hydrogen an arbitrary value of 0 volts for this reaction right here, and then they just gave every other half reaction a reduction potential based around that 0 volts that we have for hydrogen. So it's a reference for us to start from. So if you look at the chart on page 863, or at the chart that I gave you or will give you, you can see all these different potentials, and you can see hydrogen there right in the middle. Now in your problems you're going to have two half reactions, and these charts are standard reduction charts, which means that all of the equations are written as reduction half reactions. But since your voltaic cell is made up of two half reactions, they can't both be reduction. One of them has to be reduction, and one of them has to be oxidation. That means that you're going to have to reverse one of these in order to make it an oxidation reaction, while keeping the other half reaction a reduction half reaction. When you reverse anything, you're going to change the sign. And one thing that's kind of weird about this is that cell potentials are not multiplied by coefficients. So if I have to multiply an equation by 2, I do not multiply the cell potential by 2. And overall, if you add together your two numbers, you should get a positive number for your cell potential, because it should be a spontaneous reaction. So if I'm looking at an example of two half reactions, copper half reaction and zinc half reaction, and I look at their EMFs, I see that the copper has a higher reduction potential than the zinc does. That means that copper is more easily reduced than zinc is. It's easier for it to gain electrons. So that means that copper is the one that's going to be reduced, while zinc is going to have to be oxidized, which means that I have to take this reaction and I need to flip it around, and I need to take this and I need to make it positive before I can put these together into a cell. One quick way to know which one is oxidized and which one is reduced is these tables are almost always written with the most easily oxidized on top. So pretty much you're going to flip whichever one's on the bottom, and that should get you through most of the problems. Now this picture here shows another example of a half reaction, and I wanted to include this one because it's a little bit different from a lot of the others we see, in that one of the electrodes is actually a platinum wire. Now anytime you see something like that, the half reaction is not involving that platinum wire. The platinum wire is just being used to create hydrogen gas. And so the half reaction is actually the hydrogen gas half reaction. And so you may see that once in a while. So if you see platinum wire, it's probably a hydrogen gas half reaction. So let's take a look at some examples. We're going to use standard reduction potentials. We're going to calculate our standard EMF for the following cell based on the following reaction. And so we'll need either the chart on page 863 of your book, or you're going to need your standard reduction potential chart that goes with the AP exam. So if I look at my chart on page 863, I see this reaction here, which has a potential of positive 1.33. Now looking at my chart, I also see this reaction here, which has a voltage of positive 0.54. Now this part of the reaction is this reaction in reverse and multiplied times 3. Now I don't, even though it's multiplied by 3, I don't multiply this by 3. But since I am reversing the reaction to make it an oxidation instead of reduction reaction, I do need to go ahead and make it a negative number. And then I just take these two numbers and I add them together. And this number that I get here is considered the E cell. It is the electric potential of the entire cell, the whole voltaic cell, or the EMF of the whole cell. So in problems, they may ask you to describe a galvanic cell or voltaic cell, and what they're going to be asking you for is to calculate the cell potential. It should be positive if you're dealing with a regular galvanic cell. They will ask you to find direction of electron flow. It always goes from anode to cathode. They will ask you to figure out which one's the anode and which one's the cathode. The anode's where oxidation happens, the cathode's where reduction happens. They will ask you to identify the electrodes, what they're made of. They will ask you to identify what ions are present in your solutions. And they also may ask you the direction that the ions move. Now, one thing to be aware of is as soon as you turn on a battery, as soon as these electrons and these ions start to move, the cell potential immediately starts to decrease. In other words, the voltage starts to go down. So starting out, we have a cell with a certain concentration of ions with certain electrodes present, and then we turn on the battery and electrons start moving and ions start moving, and after a while, after a long while, our battery starts to look like this. Our anode starts to kind of degrade. Our cathode starts to get a bunch of gunk built up on it. The concentrations of our solution are a lot different than they were before. The electrons are no longer flowing, and the cell potential, the cell difference, has gone down to 0. In this case, your battery is dead. And we know that. We know that as soon as you start using a battery, its power is decreasing. And at some point, it's going to completely run out. That's because it has exhausted the chemicals that are available for it to use. And we'll talk more about this and why this happens later on. This right here is a great example of what they're going to ask you to do to fully describe a galvanic cell. So we're going to start out with just a basic drawing of what a cell looks like. And I look at my reaction. I see I'm dealing with zinc and copper, so I'm going to make one of these zinc, one of these copper. And I'm going to look at my two half reactions for zinc and copper to figure out which one's undergoing oxidation, which one's undergoing reduction. I see that my zinc has lost electrons, so it's undergoing oxidation, so it's my anode. I see my copper has gained electrons, so it's undergoing reduction, so it's my cathode. I know electrons always flow from anode to cathode. And I just realized I am supposed to have a salt bridge, so I need to draw that in. And it says my salt bridge contains sodium sulfate. My sodium is the cation, so it's going to flow towards the cathode. My sulfate is my anion, so it's going to flow towards the anode. So I've got everything pretty much labeled. Now what I have left to do is calculate the cell potential. I have to look at my standard reduction potential chart. So I'm looking back at page 863 again, and I'm looking for the reduction potentials for the copper half reaction and the zinc half reaction. Copper half reaction in the chart looks exactly like this, except I add 2 electrons in here, getting 2 electrons. And if I look up the voltage, it's positive 0.34. Now the zinc looks backwards because it's undergoing oxidation. So if I look up the zinc, it's a negative 0.67, so I need to flip that around and make it a positive 0.67. And then I take these two numbers and I add them together and I get my overall cell potential. And there we go, get about positive 1.1 volts, which is good that it's positive because that tells us that this is a spontaneous reaction, which for a galvanic cell, it should be positive, should be spontaneous. Alright, the last thing we're going to look at is strength of oxidizing and reducing agents. The first statement here says the more positive that your standard reduction potential is, the greater its tendency to be reduced. So the bigger the number, the more likely it is it's going to be reduced. The smaller the number, the less likely it is to be reduced and the more likely it is to be oxidized. So the half reaction that has the smallest reduction potential is the one that's most easily flipped around in order to turn it into an oxidation reaction. One thing that we are going to do is we're going to memorize some of our major strong oxidizers and reducers. This will be the last reactions set that we go through, is the big time oxidizers and reducers, things like permanganate and dichromate.